Hi, I'm Ed with Leading Edge Airfoils. My personal background has been about 10 years of Rotax engine repair, and prior to that I worked on two-cycle engines in the go-kart industry in the early 60s. Interest-wise, I've been into the ultralights for the past 15 years, where they started out as motorized hang gliders and developed into sophisticated type of airplanes that we have today. Initially, I got my interest in engines from go-kart racing in the early 60s at the age of 11 years old. I learned all the combustion engines and how to keep them running and those sort of things during that time. Afterwards, we got into hang gliding, which was a powerless flight, to the point that we were really looking for extending our flight time. So at that point, we got into powered ultralights. The powered ultralight at the time was no more than a hang glider with a power pack on it. At that time, we developed some aircraft and actually decided that we were really reinventing the airplane when we went to full three-axis control. With the full three-axis control, we found that we could improve the performance by increasing the horsepower. So we started with 10 horsepower, and now we're operating under about 55 horsepower at certain times. So we've really evolved into the light aircraft industry, and my roots have been in two-cycle engines and any kind of engine to that point. We about 10 years ago got into the Rotax engine line of aircraft engines. At that time we went and certified through the 4-day course in Vernon, BC, and qualified as a Rotax repair station. At that time we started working with the Rotax engines and started working with customers nationwide. At that point in time we were the nation's leader in parts and supplies for ultralight aircraft, and since that time I've been doing again a lot of the technical calls and a lot of technical advice to our customer. Rotax has a course where we go and qualify for 4 days, and that is good for a 2-year period. So we have to requalify every 2 years. With the leaps and bounds that have happened with the Rotax engines, we've had to go back every 2 years and really learn all the new equipment, even up to the point now where we're running dual ignitions on these engines, where we originally had a single ignition engine, and then the oil injection, which has been adapted lately to improve again the overall performance of the engine. So yes, we do have to go back and qualify every 2 years, and that is a requirement of Rotax. The heart of the aircraft is the engine in this installation. We have a lot of support groups that support it, and that is the carburation for the fuel system, the electronics where the kill switch and the ignition work. We have drive systems that drive the propeller, exhaust systems that support the engine and that area on the exhaust. We have motor mounts, kill switches, oil injection, a lot of support items that we're going to discuss in the next few segments. We're going to analyze each one independently and try to give you an idea of how to maintain those systems, how they work, and how to troubleshoot them. Now that we have the fuel system set up, we can run into some potential problems if we don't address them. One is that the vent in the tank should be open enough to allow the fuel to flow to the carburetor. If we block this vent, then we create a vacuum, and eventually the vacuum will be high enough that it will not allow the flow of fuel to the carburetor. We have in this system a tank, which is a molded tank, and the fittings are attached at the bottom. This is a crossover system. We use it to catch sediment that's in the fuel and to determine if we're contaminating the fuel with particles or pieces from the tank or actually through the transfer of fuel to the system. We have an on-off valve which is built into the side of the tank to allow us to shut the fuel off. If we had a malfunction in the carburetor, we could spill the fuel onto the ground or into the engine and create a potential problem. So we want to be able to shut the fuel off when we leave the airplane. We also have a fuel filter that is built into the system to protect the fuel pump and the carburetors from all of this material so that we don't block fuel pumps or carburetor systems. Now we'll transition to the other side and go through the fuel pump system and the carburetor. Now on the left side of the engine, where we have the fuel pump located, we have connections coming from the fuel tank coming into the fuel pump. The fuel pump is actuated through a pulse line that goes to the engine block. When the pistons are going up and down, they create a high and a low pressure. This high and low pressure activates diaphragms inside the pump and then therefore pumps the fuel into the carburetors. There are a few problems that can occur through bad installations of the fuel pump. One is that in the brass fitting on the pulse side, there is a drain hole drilled into the pulse fitting. What it is there for is to allow fuel to escape the fuel pump and not create a hydraulic locking of the pump. If the installation were that the pump was below the pulse line coming out of the engine, then you would see that the pump being down here would fill up with fuel that is the mix that's running throughout the engine. So the drain is designed to allow this to leave the engine and keep the pump from hydraulicking or locking up and not working. We still have to maintain a pump pressure to the carburetors so that they activate properly. And no installation should you ever remove the pump, as it is again having to use pump pressure to fill the float bowls to their proper level. The proper level in the float bowl is about a ½ an inch down from the edge of the float bowl. If we don't maintain this level, we run a different mixture into the engine. If the level were high, we would be running a rich mixture into the engine, and if the level were low, we would run a lean mixture into the engine. Also understand that these are reservoirs more than anything else, and then as we go to a full power situation, the reservoir will deplete. So if the float level is already low, then we may even run out of fuel altogether on a full power run. So the fuel system is secured through clamps to each one of these connections that we're using from the fuel pump all the way back to the gas tank. Anytime we allow leaking to happen here, or from aging fuel lines, usually that is the problem, then we can cause an air leak. Anytime we create an air leak where we're pumping fuel, let's say from a tank that is way down below, then what happens is we create a break in the pumping action and we won't be able to pump the fuel to the engine. So we want to be sure that all these connections are good and that we have lines that are not cracking or able to come off of the connections real easy. The thing that usually we have found in the field that affects the pump the most is the fact that vibration and heat are usually the things that take it out quickly. If you noticed, we've shock mounted this particular pump onto the off of the motor mount so that vibration is not transmitted to the pump as much as possible. The other thing that the engine does is it does create a certain amount of heat. This heat, again, if we were to bolt it directly to the engine, the heat would also cause the pump to go out, and again, vibration. So the two things that you want to keep off of the pump is the heat and the vibration. We've now gone to the point of the system working properly. If you have any more questions about the system or how it works, there is a troubleshooting sheet in the operator's manual that you can go through and trace the fuel system through and the causes for it not working for you properly. At this point, we're going to analyze the ignition system and the AC available to you as an extra power supply. This 503 Rotax has been in quite a bit of development in the last few years. What I have over here is the uprighted version of the engine, so that we can actually go through and trace the ignition system, give you a few pointers on that system and how to maintain it and troubleshoot it in later stages. What we have is a generator that is built in underneath a flywheel, and we're generating power for the ignition system. So the rotating magnet and the stators inside will generate the power necessary for the ignition boxes mounted here on the side. What we have here are triggers that trigger the ignition system through the little block magnet here that is set on the side of the flywheel. So as this block passes the trigger, it triggers the ignition system, an SCR that's built into the ignition system here, and causes it to fire. So we generate power. We then have a trigger like the points that triggers the SCR to fire the secondary portion of the coil. The secondary portion again is a double winding type system here to where we can generate the energy we need to jump the spark plugs up here. So the trigger again starts that process. It triggers it through the box. The box then releases the energy to the spark plugs. Now we have a gap in the spark plugs that we want to jump, so we have to induce a higher voltage. So the secondary windings take care of that for us. What we have is two spark plugs going to each cylinder, two of them firing from one ignition, two of them firing from a completely different ignition. So we have two boxes run by two different triggers. These triggers are getting power from a generator built in underneath that also is independent and completely redundant. So we have two separate systems. In our original engine we were running single systems with two sets of points. So if the spark plug on one cylinder was to foul, we would lose a complete cylinder. Where now you have to foul two sets of plugs to cause the engine not to operate. And again, the point system had some drawbacks in that points always wear, and that you have to come back and reset the timing at different intervals. We'll go over that particular subject a little bit later. But the dual redundant system now allows us to have an ignition system that is completely independent of each other, and hopefully again will give you that smooth ride home if you do foul one of the spark plugs. In the triggering systems we have connections that are met at different points in the system. So we want to be sure that these connections maintain continuity and don't open and bring one of the systems down. Again, remember each trigger is feeding each box, so that connection is important. And then we have a generating coil wire coming to each box that is also important. In this particular CDI ignition system, we also have to maintain ground to the spark plug. If the spark plug is not grounded, the box builds up some energy, and then that energy eventually will damage the SCR that is in the box. So we always have to create a path to ground. One of the things in installations is that someone will want to know which ignition switch is operating which box. So they'll pull the spark plugs out, stick them into the caps, and try to rotate the engine over and see the spark. Be sure that if you attempt that at all, that the spark plugs are grounded and that you see the spark going back to a ground source. If you again run the engine with, or try to pull the engine with a spark plug not grounded, the energy will build up and damage. Also, you're not going to get any kind of a spark. So grounding is required for this system to work and maintain itself. A lot of the noise starts from our ignition system. All the radio noise that you hear in your handheld radios, all of that is generated from the ignition system. So we have a large field of wires here all the way back to the coil that can generate that noise that we hear in our radios and our headsets. This particular cap is a 5,000 ohm resistor cap running a standard non-resistor plug. This is the way you get the engine out of the box and how it operates for you normally. So the first thing you do is you put your headset on and you start hearing a little bit of noise, just like if you're sitting at home in the old days and listening to a car go by on your television set or through your radio. So you start getting noise. So the first step in noise reduction we suggest is the introduction of a shielded cap. So these would unscrew counterclockwise, and you'd screw the new one on clockwise. With the shielded cap, we replace the 5,000 ohm resistor cap here with a 1,000 ohm resistor cap. We put a shielding that will slide over the back and ground against the shielded cap, and then the spark plug gives you the other connection. Then we take the shielding and run it down the line all the way to the other end, all the way down the wire and into the cap that's over here. And then we'll create a ground wire that is either grounded to 2 bolts at the bottom of the case here or to, again, the engine ground, and that will complete the circuit. At this point, we're going to show you what the outputs of these wires are doing for you. The first two, the small yellow wires with the black tracers, are for the kill switch. The gray wire is for attack output. And then these two wires are your lighting coil outputs going to the, giving you AC for conversion to DC. Now we do that through 2 different devices. Both of them being regulator rectifiers, but having different requirements. Okay. The attachment of the lighting coil to the regulator rectifier is through the first 2 yellow wires. This gives the regulator rectifier the AC coming in. The third yellow wire is not used in this installation, and the black wire becomes your 12-volt DC wire. The body acts as the ground. And also we have the fins, which generate cooling for the regulator because of the transmission of heat to the body. The body needs to be attached to a surface where it can cool and operate at normal temperatures. Now this particular regulator can be used with a battery or can be used on its own as a regulator rectifier for 12 volts DC. What we have here is another regulator that has the 2 yellow wires, again going to the AC of the engine. And then we have the color-coded red and black indicating the positive and the ground for the system. The heat sink is still built into the body, so this does transfer some heat to an airframe part or out into the air stream so that it can cool. This particular regulator is designed to be used with at least a 12 amp hour battery, and that battery creates a 1 amp load. So this regulator you would use with a battery for electric starter or normal system, and then if you didn't have a battery you would use this regulator so that you wouldn't have the battery or the 1 amp load requirement. Now we use again the 12 volts for charging the battery and for other accessories that we want to use. We warn you though that most radio systems require a special regulator rectifier to filter out additional noise so that you don't get noise directly from the engine into your radio system. The choice of regulator for this airplane would probably be this regulator, again because we don't have a battery. We're using a pull starter to start the engine. We may again want 12 volts for a auxiliary unit that we want to attach to this airplane, and this would again be the choice of regulators for this application. In the exhaust system, we have some areas to maintain. With the engine RPMs is constantly causing the pipe to vibrate. We use a spring to hold this together, because if we were to weld this together, eventually we would cause cracks, and we need to keep this area to where it's flexible. We use a high temperature anti-seize in the joint of the pipe so that that keeps it from welding together. And later stages, if the pipe is wearing, it will finally fixate itself together and actually weld. That welding effect creates leverage against manifolds and pipes and creates some braking. So we want to be sure that that joint in this area uses high temperature anti-seize and keeps the joint free. The spring is the next device that we're going to discuss, and that's the installation of it. A lot of people will grab a pair of pliers or vice grips because they can hold on to the spring and stretch it into place. We're stretching it into place over these hooks. The hooks are regular mild steel, but the springs are real strong material so that temperature will not cause them to release their tension. But if we were to grab them with a pair of pliers or something that would cause damage to the spring, we create a weak point in the spring. And as the spring ages, it will eventually break in that area. So what I use is some sort of a tool to actually pull the spring over the hook. Now be sure that as you're pulling it over the hook, that you don't drag the spring over the hook. You can also damage the hook to the point that it will fail. But if we pull them in place, they're tensioned properly. There is a tension dimension in the operator's manuals that indicate how tight the springs should be. So if we maintain that, we put the springs in position, usually we'll get a long life from them. Now because of this particular installation where you've got a pusher configuration, so anything that falls off of the aircraft usually will end up in the propeller. So we want to safety the springs or any of the devices around on the engine that may fall off and go into the propeller. What we do is we use a link of safety wire through each one of the hooks. You notice that I run it relatively loose so that we're not affecting this vibration that's going to happen between the two parts. And then at that point we want to run a bead of high temperature silicone along the spring and tying the wire along the top of the spring. This again makes it a unit. If the spring were to break and come off, we have now a safety device that keeps it from going through the propeller. This will probably keep you happy in the fact that you can lose a $200 to $300, $400 propeller every time something like this would happen. Now what we're going to do is go through the starting sequence. We want to be sure that the throttle is at idle. We want to put the enrichers on the carburetors, or if you have one of the hand primer dash types, you go ahead and prime the engine that way. We want to first tie down the aircraft, be sure the aircraft is secure. We're going to primarily set up here for a break-in procedure. So we want to be sure that the aircraft is secure. At that point, we want to be sure the area is clear. Dogs, cats, any kind of animals, anybody wants to get into this propeller. Remember, when this propeller is turning, it becomes invisible. So we're at that point where fuel is in the ignition. we want to check to be sure that the ignition is on. This being a dual ignition engine, we have 2 ignition switches. At this point, we want to engage the starter and be sure that you get a good engagement and then a good pull. The starter takes upwards of 180 revolutions to actually start the engine. The CDI engine requiring that. A point ignition usually requires a little less. But a good pull on the starter will get the engine running. At that point, we want to idle the engine at about 2,000 RPMs. So we'll check to see on our tachometer whether or not we're getting that reading. And if we're not, we want to crack the throttle a little bit and get the RPMs coming up around 2,000 to 2,500. We want to go into about a 4-minute warm-up on this particular engine. Taking the chokes off, we'll see the RPMs again rise, and then when they start to fall again, we may want to reapply them. After about a minute or so, the engine should idle on its own, looking at about 2,000 on the gauge. Then we will bring the throttle setting up a little bit and warm the engine up around 2,000 to 3,000. We'll give it about 4 or 5 minutes, and then we're ready to go into our break-in procedure. So after our break-in procedure, we'll be flying the airplane. So we'll want to go through the testing of the ignition system and some of the other things that we want to look for. Again, on this particular airplane, an instrument panel of some sort would be installed. We would have a tachometer, a cylinder head temperature, and possibly an EGT. We'll go over what we would see on those items. So now we're at a point where the engine is warming up. In our operator's manual, it indicated about 3,000 RPMs or so, where we're going to do mag checks. First thing we're going to do is we're going to shut one magneto off. We should see a drop in the RPM by indication of the tachometer, or again a sound indication that the RPMs have dropped. We'll turn the ignition back on, the RPMs will come back up, and then we will check the other ignition. Turn it off, watch the RPMs drop off a little bit, and then they should come back up again. That has tested our ignition system. Remember, we have 4 spark plugs, 2 on one cylinder, 2 on the other, independent of each other through an ignition system. So that ignition check indicated to us that we have 4 good spark plugs to start with. So we've done our check of our ignition system. Primary thing is, again, if you have a shut-off valve, to be sure that the valve is on. These engines will run about 3 or 4 minutes with the fuel that is in the carburetor. So that's just about enough to some instances to get you out on the field and into a takeoff. Be sure that your fuel system is on and that you're getting fuel through. At this point, we are flying the airplane, and with any other airplane, you want to go through smooth control movements on the throttle. What will happen if you don't do smooth control movements is, again, we remember the seizing of the cylinders from rapid expansion. So if we're throttle jockeying like we would on a motorcycle of some sort, then we can do that. What I always like to use is a smooth movement of the throttle, watching the RPMs increase slowly, watching the RPMs come off. Now, to see if the engine is operating properly or accepting throttle, we will sometimes have to give the throttle relatively quickly, a nice smooth engagement. If the engine at any time falters or doesn't want to accept the throttle, then there are adjustments on the carburetor, on both carburetors in this instance, that we would adjust to get a smooth acceleration in the engine. So again, in some instances, once the engine is nice and warm, give it some acceleration and see if it accepts the throttle. Now, if you're in an elevated area where you're above sea level, we would have already made some adjustments to the carburetor, the altitude correction. If you're at 5,000 feet, you have to change the jet sizes to make up for the mixture and the density change in the atmosphere. So we will make those changes. We can adjust to get a better mixture. We again can't adjust for the power loss that we have by going to altitude. So So we're just adjusting the mixture so the engine runs properly. Most of the time the main jet will take care of that. So when we first fly the airplane, we go through the same sequence as we do in the operator's manual. If you notice, they start out warming the engine up, running the engine at a warmer point, 3,000 to 4,000, going to full throttle, and then going back to an idle. If you think about that, that's the same thing as doing a pattern at an airport. You take off with full throttle, you crosswind, you start throttling back on the downwind leg, you go to an idle and you land. And then you give it power again and take off and go around. So the best thing you can do with a brand new engine is go out and do patterns. You obviously need to learn your new airplane, and that's the best thing to do is to go out and do touch and goes and go arounds at the airport. Do that for at least an hour or so, and that will guarantee to you that your engine is broke in properly and that your systems are working. Again, if you're having problems, the best place to analyze problems is in your system so that you see everything that's happening. If you take the engine out and send it to me and say that it's not working properly, the problem could be in the installation of the engine. And you should always analyze your engine installations for proper application. When we are looking at our gauges, we want to see the RPM being correct as far as our load. What I would do is come around on the end of the runway in a flight, give the engine full RPM with a little bit of backstick, this being normal, just a little bit of backstick to load the airplane into a slight climb. If I look at my gauge and I see the RPMs are on this particular engine about 6,500, that tells me that the propeller is properly loaded to the application, that I'm getting full horsepower. If I weren't, and let's say I was getting somewhere around 5,800 RPM at that point, then my prop would have too much pitch in it, and I would probably be loading the engine down. And understand that two-cycle engines require RPM to be correct to get horsepower. So we would be losing, for the 6,500 RPM there, we'd be losing 700 RPMs of actual performance from the engine. Plus we're dumping the same amount of fuel to the engine at that time. Our EGT would probably be low. Our CHT would be probably around normal. Remember, our CHT is our cylinder head temperature in relationship usually to the cooling system and somewhat to the mixture. So now we've got a cool mixture, we've got the right amount of air, so our CHT would probably read normal to a little bit cool. Our EGT would read cool. Remember, we're putting in too much fuel. The opposite is true if you're going in excess of the RPM, let's say to our red line of 6,800. Now we're putting in the same amount of fuel again for 6,800 RPMs. Now the engine will start to run hot, not only from cooling because of mixture, but because of the mixture itself creating this heat. The heat then will indicate again on our gauges. We may again indicate a CHT that's higher, and we'll indicate an EGT that is in excess of the regular norm. And horsepower-wise, we're not getting any additional horsepower beyond our 65. We're actually only building heat and running the engine lean. So a lean situation would happen, and we may again cause some damage to the engine. So loading the engine to the propeller and the application is very important. We'll discuss some of the proper applications of propeller in a later stage. So now we've got an engine that we've flown around, we've seen the numbers are correct, and we're happy with. So we should have an engine that will give us extended life and well to the 300-hour TBO that we're looking for. A little more about the two gauges that we have indicated to you. The cylinder head, again, will take care of cylinder head temperature. The cooling system will be blowing air back and over to the other side, and there's outlets in the housing will let the excess air out. A lot of people will be concerned of whether to run dual cylinder heads or dual EGTs. Cylinder head temperature, again, is relative to the cooling system and how it is working. On the Rotax engine, we would probably recommend that the cylinder head be put, if you're going to put one instrument, on the magneto end to monitor the cooling of the system. That cylinder head temperature probe is attached to the spark plug. If you're going with an EGT system, and in this application here we're running 2 carburetors which independently feed each one of the cylinders, we would probably recommend going to a dual EGT. Dual EGT then would monitor the mixture going to each cylinder and tell you if you have a malfunction or a problem with the carburation. If you have adjusted or changed jets, this will point out to you that the mixture is correct for full throttle and in the mid-range area. A lot of people have problems with the mid-range adjustments, and usually the EGT will give you that indication. The other thing that I like to say also at this point is EGT instruments are generally only as good as the money that you have put into them. If you go to an expense of a real elaborate EGT system, you will get good readings, but I never use them as a total indication of how the engine is operating. I will always remove the plugs and by the operator's manual determine if the color of the plug matches the reading that I'm getting from an EGT. So you'll always want to use the plug reading as your indication, and that's mapped out for you in the operator's manual. I get a lot of service calls on the fact that the cylinder head reading is not proper. On the Rotax engine, we've indicated that we want to monitor, if you're going to run a single CHT, on the magneto end. The fan system is again what we're monitoring here, the cooling of the engine, how the cooling air is affected the cylinder heads. In some of the older applications, different engines, they suggested that you put the cylinder head sender on the rear cylinder. That is again because of the design of their particular cooling system and where they feel you should monitor the CHT. Again, on the Rotax, we monitor it on the front cylinder, and that again indicates the blower condition and how the fan belt and the cooling is going over the engine. Remember that the fan is turning twice the RPMs of the crankshaft, and that this volume of air is what is taken to cool the Rotax engine. So when we're matching a propeller, we want to match it to the overall performance speeds that we're looking for. If we're looking for a slower airplane, this particular airplane goes up to 65 or so. We want a propeller that's going to pull us to those speeds. And the pitch on that propeller would be shallow, and the diameter would probably be long. If we were going into a high-performance experimental airplane, we'd probably be looking at a prop that is shorter, the gear ratio higher or lower, in other words 2 to 1 instead of 2.5 or so to 1, and a pitch that would be extreme enough to pull the airplane through the air at the speed that we expect to fly that airplane. So higher pitch, shorter diameter, and the 2 to 1 ratio would give you the fastest speed through the air. Well, every airplane is different, and the application and the engine are different, and the ratios that we can suggest for those. So in the slower applications, we want to go with larger diameters, shallower pitches, and usually higher ratios so we can swing a larger prop slower. So we have to match these to make the application work properly. Most of your applications have already been designated to you by the manufacturer. But we can improve upon it if we take the time to analyze which props will improve that. One of the latest things in the industry is the ground adjustable prop. So we get a prop that at the hub area we can change the pitch. On the ground adjustable props, we have a hub that we can change the pitch on. By sliding the protractor over the edge, we will be able to determine the angle relative to a hub laying flat on the ground. Some other types you can move the protractor and actually be able to change it and measure it actually on the airplane. But through unbolting the hub and rotating the blades, we can now change the pitch on this particular propeller. For a demonstration, we're going to show you how to put this onto this fixed pitch propeller, and we zero the gauge out, and then what we would do is slide it back off. Since the gauge is already set, we would go to the other blade, and then we would check the setting of the other blade. So we would do the same sequence of adjustments and check to be sure that both blades are in the same pitch. If your blade is out of pitch by a degree or so, what happens is that the angle of attack of the blade is at a different angle, and it will create a different amount of thrust. So what we do is we want to be sure that they're within zero of each other, so that when the prop is moving through the air, that each prop is developing the same amount. What happens is the performance changes as it would with a wing angle of attack, and it will create either vibration by the prop forcing the blade to lift a little bit harder. So it takes it out of track. The tracking then causes a vibration. Now once we've got a design that we're actually interested in, we actually have an ability now to go into different amount of blades for the application. Now the two-blade prop will usually give us the best combination of performance. It will give us the best takeoff and will give us the best performance at the higher ends as far as speeds and things like that go. If you decide that you are unhappy with the two-blade, and let's say you're looking for something that would run a little smoother, then the three-blade prop, because of its configuration, this propeller, if one blade gets out of balance, the other one is the only one that counteracts it. So vibration will occur quite quickly in a two-blade. With a three-blade, you actually have one blade with two opposing blades. The two opposing blades will absorb some of the vibration and limit the amount of vibration that you transmit to the airframe. When you get into applications where diameter is limited, then you usually have to add blades just to absorb the horsepower generated by the engine. So in those applications, if you're limited by diameter, usually you will go to more blades to absorb the horsepower that you're trying to develop. Also, so that gives you the idea between the two and the three blade. Now, characteristically, the two blade on this particular airplane will again achieve the top speeds that we're trying to achieve with this particular airplane. If we take this airplane and change it to a three blade, now we've taken the horsepower that we're putting to two blades and applied them to three blades. At that point, we have to change the pitch of the blades, usually to a lesser angle, so that we can divide the horsepower amongst the three blades. So with a lesser angle, the airplane will essentially get off the ground quicker, but will not achieve the higher speeds that we're looking for. So the three blade will give you smoother operation and will also give you better takeoff, where the two blade compromise will give you a lesser takeoff climb and a better top end speed. So it's really again determined by the speed of the aircraft, depending on that and the gear ratio. What we'll look at here is the design differences between the wood propeller and the composite propellers allow us to replace individual blades, and if we were to damage this propeller at any point, we could replace a blade and continue on. They do require that you give them the balance numbers so they can balance the prop and get it back to you. The softer composites, this particular one again is a little more flexible than some of the other composites. Again, has the claim of absorbing the vibrations and not transmitting them on into the airframe. Again, the flexibility will create a situation where they will absorb a little bit of the horsepower, where the stiffer composites will keep that from happening. This particular one is set up with a stainless steel leading edge applied so that in case you get a damaged area in it, you can repair the damage and then reapply a new piece of tape. The vibration factors again are improved in the 3-blade versus the 2-blade, and the fact that if one blade is out of balance, there are 2 others to accept the vibration. Wood versus composite. Basically, again, the wood propeller is relatively cheap to fabricate. There are a lot of design elements involved in doing that for the particular designer, but in the long run, if you're operating out of water or area where there's a lot of dirt or something, you would probably choose the composite prop over the wood prop for the damage, so that you can repair or replace the prop at the interval that you would need to.
Old Ed Wilson really knows his stuff, doesn't he? He's one of the top Rotax technicians in the country. The company he works for, Leading Edge Airfoils out of Colorado, is one of the top distributors of ultralight, microlight, and kit plane products in the world. I've ordered parts from them before and they've always treated me right.